Alright, so today I'm going to cover how to do a multi-group model in R. Additionally, we're going to go over how to do latent means analysis and calculating those weighted factor scores for participants and testing if they are different. So this will cover what the other multi-group analysis video covers, along with sort of further steps. One thing we won't cover is how to test for population heterogeneity, so covariances, variances of the latent variables, and latent means inside the sim model. And that is actually pretty easy to do if you take what I'm teaching you in this video and use change some of the constraints on the models to measure those variables. Alright, so we are going to start with examining the depression, anxiety, and stress scale and looking at its multi-group structure for men and women. So let me go to the assignment here. I am going to program a multi-group model that looks at the DAS and then test men versus women in this model, and then look at partial invariance and latent means. So, as always, start by loading the library so you don't forget. We're going to use lavaan. And if you want to create a picture, you can use semPlot. And then here's a new library I haven't used in any of my videos so far, which is fsize for effect size, that will allow us to easily calculate Cohen's d for a t-test. Fsize doesn't have nearly as many as I think BESS does, but it's a fairly easy one to run. Now, I'm the queen of effect sizes. We actually have an effect size program, so you could take all of the data and type it into our measure of the effect program called MOTE, and fairly soon we will have that MOTE capability for online. Instead of a Java-based program, we're working on it right now. But if you want to do everything in R and sort of skip the hassle, you can get an effect size from the fsize package, but there are some other effect size packages that are pretty cool as well. Alright, so let's start by loading the data. So I'm going to go over to import dataset from text file. Let me see if I can find it here. Okay, multi-group. So I have the raw data for this. Okay, so it's got a header, and I'm just going to call it data because I'm not creative with names. I import. Now, in all of these class assignments, we're sort of assuming that you've already screened the data, and so I always suggest doing a bunch of data screening first, and I had a separate video on how to do that, and then processing all of these in the sim models. But for our class examples, we just did it as if everything was perfect and screened and filled in and you had already looked at all of your assumptions. Alright, so I got my data loaded. There we go. And so I want to make sure to check the data problems. And this is, you should have done this in data screening. But since we're not doing a complete data screening, let's just make sure we don't have any issues. So I want to look at the gender variable, which is the piece we're going to run. Okay, so let me make sure. Right, so I want to do men versus women. I'm going to look at gender to make sure there aren't any random extra codes. So this essentially will make sure I have it coded correctly, so I have it labeled as female and male. And that I also don't have anybody coded randomly as 3. Okay, so that would be an accuracy check to make sure the data is coded correctly. So it is. We'll keep going. So let's enter the overall model. And so this is the model we'll actually use for all of our CFA tests. And this is just what is the structure of the DAS. Okay, and so I've got that entered here on Word. This is something that's easily Googleable too. The scale is findable online. And so I'm going to copy that and use that to program my model. So I'm going to say my model is equal to depression. Okay, is approximately, we've got question, I think it's in uppercase. Let's look real quick. Yeah, so you have to use the same column names. 3 plus question 5. Let's go a little faster. 10, 13, 16, 17, 21. Then we've got anxiety. It's approximately equal to 2, 4, 7, 9, 18, 19, and 20. And then we've got stress. So we've got question 1, 6, 8, 11, whoops, 12, 14, and 18. So that is the structure of the scale. It's a 3-factor scale where those factors are all correlated, and usually fairly highly, unfortunately. So we're going to start with an overall model. No groups. So I first need to make sure the CFA is even going to work. And so if this part breaks down, multi-group analysis is not appropriate because your CFA doesn't run. So you need the CFA part to work first. So overall.fit, we're going to use the CFA function. And so I want to put in the model name. The data is equal to the data. So data is whatever data set we've ended with last. And then here's the tricky part, because this is a normal CFA, we could stop there. But since we're headed towards a, we're headed towards a multi-group model, you have to go ahead and turn on mean structures. So if you leave off mean structures, you're essentially testing a model without intercepts and that intercept structure and means to models that do, and that doesn't make a lot of sense. So we want to leave in, we want to add in the mean structure component here. It's not going to be necessary later. If you've watched the other video, I explained this as well. But I feel like it helps if you just continue to include the words mean structure the entire time so that you know you're working with a max model, means and covariances model, instead of just covariances. So that mean structure component helps make sure that all the models match and that we're only changing one little piece at a time so they are comparable to each other. All right. So let's test that model. You gotta run the model piece first, there we go, and then test that model. So let's look at a summary here. Standardize. You can also use just T for true, which is what I tend to do because I can't spell true very clearly. By the way, R squared equals true. And so let's make sure that the questions even load on what their factors. Okay, so looking here, without looking at any of the fit indices, and looking at the completely standardized solution, it appears that we have a pretty good fit. They're all significant, but we want them to be over 0.3. It's just kind of a general rule, which relates to EFA, and they all are, so we don't seem to have any problematic questions. Now you will notice that the correlation between these three things is very, very high, which is why I always use this as an example of a great second order model, because they're all related to, you know, a generalized like psychological illness, and they tend to be very highly correlated. So that's not the greatest thing when it comes to divergent validity, but the scale does appear to run. Now, the intercepts are the average score for all of the questions, and I'm actually going to use the unstandardized solution, so that's in the scale of the variable. And so they tend to have fairly low averages, which makes sense because most of the population this is tested on is a college student population who does have depression and anxiety, but they're not at clinical levels usually. There's a small proportion of them that would be, and most of these people are not, so their scores are kind of low. All my variances are positive. And then all my R-squareds are less than 1, so no Haywood cases. So the model seems to run. Now something I've done in the last couple of videos, that if you haven't watched, I tell you to watch now, is I'm going to actually create myself an order of fit indices that I want to see. So I want to go degrees of freedom, I want to get chi-square, okay. I want to get REMC, SRMR, and CFI, because it's my favorite mix of the alphabet soup. And I'm just going to run that. So I've concatenated a vector of fit indices. And then what I want to do is now get the fit measures and get them for overall.fit. If I just run this, that gives me all of them, which is really great and wonderful, but I don't want to see all of them. So if I tell fit measures and then do fit dot measures, because that's not confusing, tell it to just give me that order, it will give me just the ones I want to see in that order. So that makes it kind of a little bit faster for you to look at just the particular ones you're interested in. So you could pick, if you aren't sure how they're spelled, run fit measures without that component and then look at the spelling of them. These are the names that you would use. Alright, so let's start filling this in. So for my first model, I have 186 degrees of freedom, and it's 547, 99. Second, so 69, so a good room C, good RMR, and we're pretty close to a good CFI. And this here should also be here. There it goes. Okay. So I would say this model's okay. It seems to be appropriate. Now, it would probably help if I had done some data screening on this, because that could eliminate some outliers that may be causing some of the poor fit. But we're going to keep going. So the next step is to test each group separately. And so I want to know if each piece, each subgroup runs okay. So it may be that some of the poor fit statistics, now these are pretty good, but if you have poor fit statistics, it may be that one group runs okay and the other group is horrible. And then that's where you would really stop. So you'd separate the groups out and go, look, this one works great. Oh, this one doesn't work so great, and speculate on why. So let's test each group separately. So I got to subset the data. You can't use the group function in CFA that nests them together, so we want to do something separate first. So let's make a women and a men data set. Not menu. Nope, nope. Studio is great. Sometimes it's helpful when you don't want it to be. Alright. So for the women data set, what I'm going to do is do subset. I like the subset function. It's pretty easy to understand. I want to subset my data set. And I want to subset it where the column gender is equal, equal. Remember, this is a logical operator, so it has to be double equals. And the code is female. And if I rerun that table real quick, I should get 246 participants in this data set. So come over here, look at women, 246. So always check and make sure your subset did what you expected it to do. Because it's easy to leave out an equal sign, and it looks like it ran, but it didn't actually do anything. So I'm going to do the same thing for male. Should get 165 people. Object min, oh, right. Gender. So it's easy to make that kind of mistake too, 165. So let me show you an example of a mistake. So let's say we had actually just said where gender equals male, because that is a very easy thing to do. What it will do is it actually just copies the data set for you. And so if you notice up here at the 411, it included the females, because it didn't really know what to do. So make sure your subset does what you think it does. Okay, so let's fix that. And now men only has the men group. So always make sure your data set is subsetted in a way that makes sense. Okay. Now let's cut and paste this. We're going to use this and just change it as we go. Let's do women first. So I'm going to change the names of these to match what I'm kind of trying to get at. So it's the women fit, so I need to run this on the women data set. Now I want to get a summary of that fit, just to make sure nothing looks too nuts. So everything looks pretty good. If I were doing this for real analysis, I would go back and check on each level, but to save some time here, let's just look at fit measures. And we'll see that the CFI is not so hot for women. And they are the larger group, so that's a little surprising. It's hard to get guys to do research sometimes. Okay. So we got 186. It's going to be the same degrees of freedom because it's the same model, just with a smaller subset of the data. 0.081, 62. So, okay, still okay for the residual statistics. That CFI is not so good. But overall, the women's data set is all right. It's not too different. You wouldn't do any test you couldn't use a nested chi-square test because it's the exact same model, so they're not nested, they are the same. And I could do a change in CFI model, but I'm not really wanting to know if women are different from the overall model, since the overall model is a weighted average. Mainly want to make sure that the whole thing doesn't crash, and it looks it looks appropriate, like, okay, it's not that different. And generally this is just kind of a guesstimate. Most people don't really actually test them against each other. Okay, so let's do the main group now. So we're going to take this. Now, when you are cutting and pasting like I am, it is easy to forget to change something. But when you get the exact same fit statistics, be very suspicious. If they are the same down to, like, all of them are exactly the same, you've probably run it on the wrong data set or forgot to change one of your summary statistics. So when you get the exact same numbers, usually something's wrong. Not always, but usually. All right, let's try min now. So their summary, so their questions appear to load. The variances are all positive. So their questions are actually doing pretty good. So nothing crazy. Let's look at the fit statistics. Okay. And they're all right too. So at 186 is 474, 097, 066. So they're a smaller group. So we tend to have slightly worse fit. Okay. And it's okay. So our model with everybody together is, better because I have more people to estimate from, and more people will usually always give you a better fit if it's a good model, because you have more observations to estimate from, and so the more people you have, the better of an idea of what's going on you can get, especially because you get more normal distributions, and it's just sort of easier to estimate when you have lots of data to estimate from. But our male and female groups, while these CFIs are not so hot, are pretty good. Okay? You might have problems if this were your model, convincing people that multi-group models are doable because of those CFIs. Like, it tends to be a pretty strong, people feel about 0.9 being the kind of cutoff. But these are okay. And it would be interesting to know if there are differences in the scale based on what group they're in. Okay, so let's keep going and try the multi-group steps, because this is an example. So we've tested each group separately. Now we're going to get really into the multi-group part, and that's where configural invariance comes in. So let's start there. And if you haven't watched the other video, I'm going to use the Brown steps and Brown terminology. This is Timothy Brown, and his book is Confirmatory Factor Analysis for Applied Research. And I think the new version of the book that just came out actually has lavaan code in it. Mostly his code is like M+ and Lizarol. I think it's Lizarol. And it's a fantastic book that really covers lots of interesting pieces to scale development, and while the steps for multi-group models tend to vary across research labs and the terminology definitely varies widely, I'm going to go with his terminology because it's kind of become the more popular way to talk about it at least in psychology. Okay. And we've been publishing using this terminology and people are accepting it, so I think we're probably okay. So I'm going to stick with his terms. So the first one is configural invariance. Sometimes this is called equal form. So this is where we're going to take the men and the women groups that are currently programmed separately and smush them together into the same model. So there were a lot of examples about pancakes in the previous video, which I won't do again. But basically, I want to know if I take these two separate models and combine them into one model, does that work? So this is called nesting the models together. We're basically stacking them. So we've got men, we've got women. And we're not going to force anything to be equal except the picture. So we want to create the same picture of the data. And we'll do a real quick plot right here just to show you what I mean by picture of the data. Alright, so I'm going to go back to this original overall fit one and copy that because it has the data set. So now I want to make sure I've gone back to the full data set, or this will be very cranky when you run it. So let's do configural model. So I've got mean structure equals true. Now we're going to add something new to that. And what that is the group variable. And so we're going to do the group here as gender. And so we want to leave on mean structure as true. So this component, because I added the group piece here, is no longer necessary. It will automatically do that when you add the group piece into it. But I feel like it helps if you keep the same code the entire time. So I'm just adding this on, and I'm adding this, and I'm adding this. And it really makes it obvious that the entire time is a max model. So we want to leave in means and variances for the whole thing. Means and intercepts, sorry. And so I'm going to leave that code in here because it doesn't hurt me. So I can leave it in without any problem. So I'm going to leave it in just so you know, like conceptually, like theoretically, here's what I'm doing. All right, so let's try with it grouped. Let's change this. And then, yep, this one too. All right. So when I look at my summary, what's going to happen is it at the top will give me the chi-square value for that particular model, but it also gives me men and women separately. Now don't let that confuse you, because while those are the numbers here, it will not give you all of these numbers. Okay, so to get the rest of your fit statistics, whichever ones you're picking, you have to run them separately. It does give you the chi-squares for the groups individually, but that's it, as far as I'm aware. So when we run fit measures here in a second, you'll see that we'll only get one set of fit measures for those two models nested together. The next thing it's going to do is show me all of the loadings for each group separately, and now right now they're allowed to be different. So question 5 for women is 7.51. If I scroll, I should get down here to men, and for question 5 for men it's 0.843. So the two groups are forced to be the same picture, but not the same loadings. Okay, we're allowing them to be different from each other. Okay. I can go through all these different statistics. And then real quick, let's make a picture. So it's the semPaths function as part of semPlot. And let's make it for the configural.fit model. I'm going to use what labels, and that will put in the standardized loadings. If you do PAR, that'll give you the non-standardized loadings. And then layout, there's 5 or 6 options, but tree is probably my favorite for CFAs. And when you do that, it says, okay, hit enter for the next plot. And it will give me each group separately. Now, it's not the prettiest picture, but, you know, it's worth the trouble. So you can see that it's a means and covariances model because it has the little triangles for intercepts, which are the means for the questions, and the means, the intercepts for the variables are means for the variables, which we force to be 0 for to make this model identified. Covariances, so otherwise it looks like your normal model. Okay, I'm going to hit return to get the next plot here, and then it'll also give me group 2. Okay. So we've created the correct picture of the data. So we've forced these two models to have the same picture, this picture, but we've not forced the loadings or anything else to be the same. All right, and then last but not least, let's get our fit statistics to put in our little table. Right. There we go. So we're going to double our degrees of freedom because we get to count the manifest variables twice because they are in both models. And then RMC is all right. SRMR is good. CFI is still not that good. But overall, this model is not really that different from the other models that we've created. So men and women can be put together in the same model without explosions. Now let's try constraining different pieces one at a time to see if those models continue to be the same. So this works in the backwards order from if you watch the latent curve video or an MTMM where you're sort of turning things off and on. What we're going to do is start with the least restrictive model. Like people can do whatever they want, and work our way down to a more constrictive model where we're forcing things to be more and more equal to see where it breaks. And if it doesn't break, what does that mean? Well, if all of these steps go well, that implies that the scale that we're using is sort of is applicable to both groups. They have the same loadings, the same intercepts, the same error variances. So you can be assured that if you give it to a man and give it to a woman, minus some random individual differences, the scale is taken in the same way. If we find differences, that implies that there are some things about the scale that is inherently different across groups. And to me, the best part about scale development is that both of those are interesting questions. On the one hand, I would really like it to be totally invariant, which means not different, so that I know that this scale works the same for all these different types of people. On the other hand, if they are different, that's really good to know, because then you can account for those differences, and the total score, or your latent mean score, or if you create a weighted average, can be fixed for those differences. So let's say you find a difference in men and women on depression, because that's pretty common. Is that because of the scale that you're giving them, or is that because there really is a difference? Well, running this type of analysis, I can tell you that the scale is invariant. So there's a difference, or there's something else, some other third variable involved, because science isn't perfect. Wow, brain fart. Oh, or I could say, well, yes, there's this inherent difference on this scale, but if you account for that, we no longer see differences, or we still see differences. So I think multigroup modeling is like super cool stuff, but my area is also scale development, so I'm getting my bias there. All right, so let's try metric invariance now. So what metric invariance does is it takes that configural invariance fit, take out this picture here, and forces the loadings to be the same. So we've got the same picture. Now we're going to force the loadings, or in this clear picture, these little lines here, to be exactly the same. Okay. So do the items, the manifest variables, have the same weight to the latent variable? Is what we're asking. And to do that, first let's rename it. What we're going to do is add one more piece here. So we're going to keep adding to the CFA part. The next two lines don't change just a whole lot. And what we're going to add is a group.equal function. And that is going to force the groups to have equal whatever's you tell it here. So I'm going to concatenate a list, because we're going to end up with, or vector, we're going to end up with a bunch of these as we go. And the first one you want to try for metric invariance is loadings. Okay, so metric invariance means we're talking about the loadings. So are the lines the same? And let's see. Okay, so that ran. And so how you can tell what it's done, let me scroll up to the top here, is we get these new little things here. So we have forced these to have the same loadings. Now, question 3 just kind of gets stuck because it's been the same the whole time, because it's the one that we've scaled on. But we've forced them to have the same loading. So this one particular loading is called P2. So let me scroll down. Let me see. It's 0.811. Let me scroll down to the min group. Here's P2 again, 0.811. So we've set them all equal. And equal is a weighted average, essentially, between the two groups. Now, when I do that, does that break the model, essentially? So let's look at the fit statistics. What we're going to do is see if that messed up our model. So my chi-square is not too different. You'll notice we got different degrees of freedom. So the degrees of freedom will go up because we are slowly constraining things to be equal. So we've taken what was 2 estimations and made it 1. So we'll get more degrees of freedom back. And the most popular, at least in our area, way of testing if they're the same is by using the change in CFI. Jules Chung and Rensvold, sorry if I've mispronounced your name. They have a paper from 99, 2000 or 2001. They've done several papers on this work about partial invariance. Highly suggest reading them. And so their argument was that the chi-square nested test is notoriously problematic due to sample size and a lot of other things. So what should we use? And their suggestion was a change in CFI. And so the change in CFI needs to be less than 0.01 to be considered the same. Okay. Let me add this here so you know what we're doing. So we're testing loadings and, oops, sorry, this is not loadings. Oops. This one is the picture, right? And then this one's the loadings. So the change in CFI has to be less than 0.01. Equals those models are considered approximately the same. Greater than 0.01 is different. And I would say less than or equal to 0.01. If it's right on 0.01, most people consider that okay. So what I'm going to do is subtract 842 to 837. That's 0.005. So I would say that that is not different. Okay, so since we're working our way down, we're going to compare a model with no restrictions to the model with one set of restrictions on the loadings. So you're comparing to the one directly above it, and it's not different. So when I constrain those loadings to be the same, it's okay. So that implies that the loadings for men and women are roughly equal, which is good. That means that they have the same picture of the data and then the same weight to their latent variables. So now, let's try scalar invariance. Okay. So scalar invariance is when we're going to look at the intercepts. And then just from my previous work in this and the couple papers I've published, generally, if it's going to break down, this is where it's going to happen. I can't remember if it does in this model or not, but generally it's scalar, so the intercepts are the problem. And so what are the intercepts? Well, the intercepts are the average question scores for those items, those manifest variables, and that's really easy to have differences. So looking at this question, women tend to answer this one at with a bigger number than men. So if you have a 1 to 7 Likert scale or 1 to 5, and men tend to pick 2 and women tend to pick 4, but it has an equal weight to that latent variable, this is where it will break down, and it'll show you that men pick lower numbers than women. So to add that metric fit part in, so right now it's just the loadings, we're going to do comma and add in the term intercepts. So that will test if the loadings and the intercepts are both invariant. So you'll notice from one model to the next, we're just adding one piece as we go. So we went to the same picture and the loadings, now the same picture, the loadings, and the intercepts. So we're adding, it's not one path, but it's one component at a time. So let's try that. So under the summary, what you'll see is now you'll have a bunch of numbers here at intercepts because we're forced the intercepts to be the same. And then let me look at my fit statistics to see what happened. Oh, just kidding. Let's try a word here. So I've got 408, oops, 8 is 341. Right, 0.087, so that one didn't change. 0.76, 0.829. And what I'm going to do is subtract from the previous step. So I don't want to compare that to configural invariance because there's two things that are different. So it's from scalar to configural, we're talking about the loadings and the pictures. So I want to compare only to the one directly above it, which would be metric invariance. So I'm going to do 837 minus 829. It's 0.008. So that did not break. Cool. So it's still less than 0.001. I'm sorry, 0.0110. And so nothing happened. So now I know that not only are the loadings the same, the intercepts are also the same. So let's keep going. The last one we're going to do is strict invariance. And some people argue you shouldn't even do this one. I think it's an interesting question. I'll explain why here in a second. So let's add that in. So strict invariance covers the variances, the error variances, so the residuals for the questions. And in the picture here, okay, so this would have been the intercept number out here. This, we're talking about these double-headed arrows on each of the manifest variables. So we're testing if they have equal variances, error variances. So what you're going to do is under intercepts, next to intercepts, you're going to add in residuals, because that's what those are called. What does that mean? Well, when you have different residuals, that implies that the spread around the intercept, the average question score, is different for each group. So what does that imply? And I always think about this as a question of kurtosis, like how different is the spread for each group. So let's say that everyone's intercepts are equal, because they are. So men and women are both picking an average of 3 on this question. So if it's a 1 to 5 scale and I have the mean as 3. And so everybody has the same mean, because that was what we tested in the previous step. Now if I find differences in variances, and men's variance is 1 and women's variance is 2, that implies that men have a variance of, or an intercept of 3 with a variance of 1. So that means that their scores in general are from 2 to 4, so 1 down and 1 up. If women have a variance of 2, that implies that their scores are 2 down and 2 up. So they're going from 1 to 5, whereas men are only going from 2 to 4. And so it implies a different endorsement along the measure of the scale. So women are getting a bigger spread in this example. And so they're picking more of the items, a wider range of items than men. So even though they have the same average score, that average score has a different distribution. And that's a really interesting idea in the sense that you get a wider range for women in that example than men. And so let's see what happens. It could be that everything works totally perfectly. It doesn't, otherwise this would be a silly example, but let's look at the summary. And so now our variances are set to equal. Okay? Not the variances at the level of the latent variable. That's the population heterogeneity thing I was talking about at the beginning. We're just doing variances at the manifest variable level. So let's look at our fit statistics. So we've got 429, oops, wrong one, equals 112, 0.088, 0.080, 816. Okay, so I think we're going to be in trouble this time. So I'm going to subtract just from the one above it, just like we've been doing this whole time. 0.829 minus 0.816. 0.013. So yes, that is significantly different. Duh. Okay. So that didn't work. So what we're going to do now is try partial strict invariance. So what partial invariance is like pretty much how it sounds. What we're going to do is test if we can figure out that it's just one question or something. Let's say we find this difference, which we did. Maybe it's just question 4. Okay, so it's just one item that we have the problem with. And so I think about partial invariance as sort of like little t-tests, like let me figure out where the problem is. So I found a problem, and it's just kind of like ANOVA, like, oh, there's a difference somewhere, and then you're like, okay, but where? So a partial invariance figures out the where and determines whether or not we could, if you account for this one problem, get back to saying the rest of it is invariant. So it's sort of like sussing out where the difference is, and if there's only 1 or 2 little differences, saying, well, it's mostly invariant minus these questions. Now, how many items you can set to like let be free and not be constrained? I always kind of go with 1/3 of the scale. After that point, you're talking about a big chunk of the scale is different. There are no hard and fast rules for that. That's just a judgment call for you, depending on what your goal is for the analysis. Okay, that being said, what we're going to do is figure out where the problem is. And to figure out where the problem is, we're first going to run modification indices. So mod indices on that last model. Now, if you do that, what you're going to get is like, oh my gosh, so many things, 500 or more, okay, different ones. And the more questions you have, the more you'll see this. And so let me give you some general rules of what you're looking for. Okay. For if your model breaks down at metric invariance, you're going to look for a operation that is equals to tilde, because that is the loadings. That's how you set up loadings in lavaan. If you are testing scalar invariance, you're going to look for tilde 1. That's for the intercepts. Okay. And that code is all explained on page 27 in Buchanan's book. If my model broke down to strict, which it did, we're going to do double tildes for variances. Okay. So that's what we're looking for, is 2 tildes. So the first thing you got to do is save the modification indices somewhere. Okay, I'm going to call them partial mod for my partial step. Right, I've saved them. It does give you this warning that it doesn't happen, it doesn't tell you about equality constraints, but that's okay because we're just trying to figure out where the problem is. So I want to find only the partial modification indices that are variances. So give me just the variances. So I'm going to subset out the data. So partial mod, see if this works. We want to use, what column do we want to use? Well, let's look at partial mod. Okay. And so this OP column here for operation is the one we want to use. So if I look at all the variable names, which is using the ls function, I can see that there's this OP variable name. And so what that does is it's the operation. So I want to subset out the data where partial mod, the operation, so the operation column, is equal to double tildes. Okay. And so I want to just get the double tildes. So I can do that. Let's see what variances has in it now. So there's still 400 items, which is no good. And then I want to find the biggest one. Okay. Well, you could order the variances, and let's try that real quick. Okay, so one of the easiest way to do that is to do the order function. So I want to order that variance piece, but based on what? So if I try to look in the column, look in the rows, give me all columns back, that is going to have a moment because it doesn't really know what to do with what you're asking, right? So I've got to order it by a specific column. Okay, so what column do I want to use? So let's look at what's in variances. Okay, and we're going to use the MI column. So what is the MI column? Well, that's the modification indice. So we want to get the largest change, or the largest modification. So I'm going to use the $MI. Okay, so that will order those variances. The other thing you probably want to add is decreasing equals true, because I want largest first. All right, so that gave me smallest to largest. But now the issue is this one. So I have question 1 to question 12. Well, that's telling me I should correlate question 1 and question 12, basically the errors. But that's not what I'm looking for. I want to look for where there's a problem with a question to its own question. So basically, I want to see where 9 should be correlated with 9, because 9 is restricted, it wants you to do something in that question because it's got the largest problem. So I essentially want it to be where the left-hand side here, so the left-hand side of the operation has the same code as the right-hand side of the operation. So I want to take out all these ones where they're different things, so 1 to 12 here. So we're going to do one more subset, and you can do these together. I just was trying to show you my train of thought of how this is working. So I want to subset out the variances one because I relabeled it. So if you want, I can call this variances 2, kind of keep it straight, where the left-hand side is equal to the right-hand side. Okay, so I want left-hand and right-hand side to be the same. And there are several ways to do this subset function. I just like subset the function. Now, we're on a much more manageable 48 items, and the biggest one is on top. So it's question 21 to question 21. Now that's for group 2, so 21 will appear again for group 1 somewhere, but since it has the largest problem, it's the one I want to use first. So that's how I got to which question first. So let's actually try that partial invariance now. So I'm going to copy my strict invariance code, and then I'm going to change this to partial strict, because that's where we're at. And then I'm going to add one more piece out here. So this is going to be new, so comma, and it's group dot partial, because we're working on partial invariance, so very convenient name. And what I'm going to say is I want to let this particular pathway be unconstrained, which means it's going to be estimated differently for each group, or be free. And the cool thing about pulling these modification indices, since they're written in lavaan code, is you can cut and paste the highest one into, sorry, you want quotes first, into the group.partial piece. So it's basically saying let this particular pathway be different across groups. So that's nice. Now, when let's say you have a problem at metric fit or scalar fit, you just want to look for the largest one. So the being equal on both sides is specific to strict problems. For metric, it is just whichever loading is the problem. And then for scalar, it's whichever intercept is the worst. All right. And modification indices, if you aren't aware, is a chi-square change, and so you want the larger values. It's always positive. Okay, so I changed and I'm going to let question 21 do whatever it wants. So let's look and see what happens. So if I look at the summary, let's look at question 21 here. So for the variance, 0.22 is men, I believe. Yes, so male. So the male group for question 21 is 0.22. For females, it's 0.127, and that's significantly different. So women have a smaller range of answers, and men have a larger range of answers for that question. And you would pull out the scale and look at that question and see if you can understand why. But at the moment, what we're going to do is see if that solved our invariance problem. So this is particularly question 21 variance. And we'll have one change in degree of freedom because we just let one question be different. 8, 9. So let's see, is that different? Well, we want to subtract from the scalar invariance step. And so basically this step is kind of like, okay, that didn't work. So let's try fixing it and see if our partial model can be close enough. So we're going to take 829 and subtract 819. And that is easy math, so it's 0.010. And I'd say that's not different because it's right on the line. This is like getting p equals 0.05, and you're like, phew, right? Or 0.05 001 or something. So we're right on the line, but it's now considered not different. And so I would go back and talk about interpretation for this question. So question 21 variance is different. And then, so for men, it was 0.222. For women, it was 0.127, I think. I'm just trying to remember off the top of my head. And so that implies that women are endorsing a smaller range than men. And then I'd also look at the average for that question. Under intercepts, where's 21? Okay, so the average score for that question is 1.146. So that means on average, women are going from about a 1 to 1.2 something, whereas men are going slightly below 1 and 1.3 and 4. Okay, so we're getting a bigger spread of the variable. You can kind of think about this like standard deviation. That's its variance, but it's kind of the same idea of like, here's the average difference from the mean. All right, so interpret my findings. Are the groups invariant? Mostly. One problem with question, 21 variance, and I already talked about what does that imply. Now here's the part we're trying to get to. So that up to this point we've done the same thing as the last video. It's a little faster. And now I want to talk about latent means and standard deviations. Now I could test latent means within the lavaan code by using the means, by telling it to test if the latent means are roughly equal. And that is a perfectly valid way to do it. But often what will happen is you have all this data. You have all these weights for how related it is to the latent variable, and what you could do is transform participant scores to weighted scores. So what I'm going to do here is a way to test if the weighted factor means are the same across groups. And so you could do this, like I said, within the structural model is a really common way, but this is the other common way that's a little bit trickier to do. And so what I'm going to do is create a weighted data set. And often what happens is people will test if the means are different and then use those weighted scores to do something else. So I could take these weighted scores and use them to predict some other variable that I have in my data set. And that's often the impetus for doing this, is having it using weighted scores to predict something else, because weighted scores tend to work better, because some questions are better than others. So let's calculate the weighted scores for participants, and this is where it gets tricky. So I'm going to call this latent means because in theory what we're calculating is a latent average. You could do a latent total, but really these are weighted scores. Alright, so one thing we want to do is use a new function called parameter estimates. So what parameter estimates does is it shows you in a nicer layout all of the numbers that you normally get out of the summary function. Okay, so the parameter estimates is the summary function in a layout that's actually very similar to modification indices. And so we've got the left-hand side, the operation, the right-hand side, what group it is, the label, the numbers. And we're going to use the, now I did this as a scaled, I scaled on the manifest variables, and so I'm going to use the unstandardized solution here. You could use a standardized solution, you just need to tell people which one you're doing. But I want to use those, so I'm just going to save it as loadings, so I can manipulate it and use it. So let's get, so I've saved the loadings. Let's get the men and women loadings differently, or separately, so to speak. And the reason you want to do that is if you had a problem at the metric fit level, where the loadings were different, you wouldn't want to just take the loadings and multiply them by the data set because they are different things. Now in our data set, the loadings are the same, but I'm showing you kind of like the way that you could use the code that you could use no matter which way it broke. So let's separate these out and get just the men loadings and just the women loadings. Now that means you have to remember who's group 1 and who's group 2 because it does not use the labels, which is awesome. So what I'm going to do real quick is run the summary function for that partial fit model. And whoever's pops up first, sorry that was scrolling really fast. Here we go. Whoever pops up first is group 1. So the female group is group 1. Okay, and so group 1 is female. So let's actually do women first. Sorry guys. So I want to subset out my loadings. So I'm going to say give me just the loadings where the group equals 1. Okay. And what that will do is give me a data set where all of the group labels are just 1. Now, we don't actually want all those labels, but we're going to do another subset. Let's do, now we're the group equals 2. So I have men and women subsetted out. Here's the issue. I want just the factor loadings, because you're not going to use the variances and the intercepts when you tend to do this. You multiply by just the factor loadings, and you ignore the variances and intercepts in this type of analysis. So I actually want where it's group 1 and single ampersand, which is above the 7, where it's just the loadings. Okay, so that's where the OP column, so for operation, is going to be equal to equals tilde. And so what that's going to do, now if I look at women load, is give me just the loadings for the questions, which is cool. Awesome. Now, here's another issue. Let's do that here. And OP equals tilde. So I have just the loadings. So I have the loadings for women and the loadings for men. All this data is great, but I just want the estimate. Okay, so I just want this estimate column because I just need a vector of numbers. Okay. So what you can do is actually the select function. It's part of subset. 2 S's there. And select will allow you to pick specific columns. So I just want the estimate column. So select equals estimate. Now, that's going to lose some data that we're going to need here in a second, but let me show you what that does for you. So now if I look at just the women load, it gives me, ignoring the numbers here, that is not the number of the question, that's just the row number. It gives me all of the estimates in order for both of them. So now I just have a vector of numbers, and that's what I needed. Here's the tricky part though. When we go to multiply these out, so now I want to take those loadings and multiply each participant's individual score times those loadings. So what I'm doing is I'm taking the loading times the participant actual number they picked and creating this weighted column. Okay. I have to make sure the questions are in the same order. So what we're going to do is multiply the loadings by the participant scores. But first, this is super important, so lots of exclamation points. Make sure the columns are in the same order. More exclamation points. So let's check something. So I'm just going to run loadings again and look at what order they're in. And I went back to the original set of loadings to show you this. So here they are. This is the order right here. So I've got 1, 3, 5, 10, 13, 16. And that is the same order that you wrote them in here. It just gives them to you in the order that you typed them in, essentially. So here are the order of the questions. So I don't need the little pluses here, but that's just my code, so that's the order of the questions. Now you want to look at the data set. And look at that order. So my data set, what I'm going to do is use the women data set because I subsetted it out a minute ago, so I can use it. That's why I didn't call any of this women yet. So let's look at just the first 6 rows of the women data set, and that's the head function. Here's the question order for the women data set. Now I want to make sure that those match, because what we're going to do is multiply the loadings times the questions. And if you multiply the loadings and they're in 1, 2, 3, 4, 5 order, and the questions are in 1, 5, 8, 12 order, you have now totally screwed that thing, because you want the loadings to match up with the question. Otherwise, you're multiplying a loading for a different question times the score they actually wrote. So that's no bueno. You want to make sure you multiply the loadings and the questions in the same order. Okay, this is super important because mathematically this will still run unless you screw up column stuff here, and you will not know. So make sure that these are in the same order. And they are, because I tried to make this example easy. But if they weren't in the same order, what you can do is when you're typing the name of the data set, so I have the data set name, I'm going to use the brackets to talk about the data set. I want all rows, so leave the row space blank, and then in the column section, just reorder them. Right? So I could say I want to do question 3 and then question 5 because they have names, and then question 27, like whatever order. Or you could do, if you're like me and like column numbers, the numbers, etc. Okay, this way is probably a little better because it even if you rearrange the data set, would force them to be in the same order, but if you're not rearranging your data set, you could use column numbers. Okay? So if they are in the same order, you have to put them in the same order. Okay? And you would put this code that I just typed out here, my little example. It's a very small example that would actually be much longer, right? You would put that code in this next portion. So what we're going to do is multiply. If you are not good with matrix algebra, that's okay. But one of the big things about matrix algebra is that the columns, the way they have to be multiplied together, the inner two numbers have to be the same. Okay. So what I'm going to do is use the dim function for dimensions and look at women load. Okay. So women load is a 21 by 1. So 21 rows by 1 column. And then I'm going to do the dim function and look at just women. Okay. It's 246 by 23. So 246 is how many rows there are. Now we're going to use the apply function to do this. Now apply will do 1 row at a time. And so that would make it 1 by 23 because we would do that 246 times. Okay. Here's the issue. One of them is 21 by 1 and the other one is 1 by 23. So we've got to drop those first 2 columns. Okay. So what I'm going to do right now, I'm going to actually just drop out the first 2 columns. And why do I know it's the first 2? Look, here's gender and race at the beginning. So I'm just going to dump those out. Or actually, you can leave them in. We'll dump them out here in a second. But you want to make sure that you're multiplying in the right direction. And so we're going to actually use the transpose function here in a second. But making sure that they're the right dimensions. Because if you try to multiply things that are different dimensions, you will get a very strange error. All right, all that stuff, let's talk about how to actually get the multiplication to happen. So let's do women multiply. We're going to use apply. So remember, apply lets you do the same function over and over again by rows or columns. I'm going to do this by rows. So I want to use the women data set to match. I want to do all rows. And then I got to drop those first 2 columns. So I'm going to say minus for drop 1 and 2. Okay, or 1, 2. And that should drop the first 2 columns for me. If you aren't sure if that's going to work, just try running it in the console. Oops. And I should have included the head function, but you'll see that it dropped columns 1 and 2 for me, which is good. I wanted that. So now as part of apply, I have to tell it rows or columns. I want to do this by rows. And then this part is the part where I just sort of made something up here. So I'm going to do a function. So in apply, you can make up a function. Because normally with matrix algebra, you just tell it to multiply the 2 matrices. But since I'm wanting to do this across, it doesn't quite, often R will just repeat the process over and over again, but if I try to multiply these 2 together, because the dimensions are not the same, 21 by 1 and 246 by 21, because we dropped those 2 columns, it kind of goes, and doesn't know what to do. Okay, since we're dealing with matrices and not vectors. And so what I can do is tell it to apply. So I'm now fixing the problem where it's 21 by 1 and 1 by 21. So the inner two numbers are the same. But there's not really a function that's like, just multiply, damn it. So I'm going to make myself a little function. And what I'm going to do is say multiply x, which x here is going to be this women data set by row. So you do function x, and so I'm going to take that x and multiply it by its loadings. Okay, so we're multiplying the data set, women here, by their loadings. So I'm going to put women load in here. And that is my hack at doing this. There might be an easier way. If you find an easier way, shoot me an email, and I will do a video for that to show you how it's easier. But so far, this has worked pretty well for me. So I'm going to tell that to create me a data set where everyone is multiplied out. Now, the cranky pants part about that is that you're going to lose the column names and stuff. So what happens is it actually creates you a list of every participant and their estimates multiplied out. So this is a really great way to check like the first row or something to make sure you've done it in the way that you expected to do it. And let me go ahead and do min also right here. Apply min. We want to do basically the same code. We want to drop those last two columns, or the first two columns. Actually, let me show you what happens if you don't do that. And you will see that it will not be happy with us. Oops, X. It's going to be the exact same code times min load. Right. Non-numeric argument to binary operator. Yeah. Super unhappy because the matrices are different sizes. Right? Because one of them has 23 columns and one of them has 21 rows, and those need to be the same. So let's make it happy. I couldn't remember exactly what the error was, but this should work. There. Okay. So the issue here is that I wish it would just tell you, hey, I can't do matrix algebra on this. You suck. But it doesn't. It gives you an error message that I'm sure makes lots of sense to the people who programmed it, but that usually means that your matrices are not the same size. All right. So now I have them multiplied out. What I want to do now is combine them together into a data frame. So what we're going to do is coerce this list of all of these multiplications into a data frame. So we're going to make it not be a list because the list is problematic. So what I want to do is, you can call it women data. I'm going to keep calling it women multiply as data.frame, women multiply. Okay. So I'm going to coerce it into a data frame. So when I do that, let's look at it now. Now I have a very strange looking thing. So let's look at the dimensions of that. When it coerced it into a list, it made it 21 rows and 246 columns. So it takes each list and just stacks them next to each other like little dominoes. And that's great because I have the data I need, but it's in the wrong shape. So it is now 21 rows for each of the questions and 246 columns for each participant, which is not the way we tend to think about data. So what we're going to do to fix that problem is transpose the data. So I'm going to take women multiply and use the T function for transpose and just flip it on its side. So let's look at that again. Now it's 21 columns and 246 rows. Okay. And that's what we want. So there's a little bit of work getting to these numbers, but once you do it once, it's not so bad. So let's do min the same way. Coerce it into a data frame. And you can actually combine both of these functions together. I just think sometimes it's easier to show you how I did it one step at a time. And if you accidentally transpose it twice, just transpose it again. So it always helps to look at the dimensions. Okay, so, Ooh, that did not do what I would have expected it to do. Right, so my min multiply data set has 144. Oh goodness, what happened? Well, I did something wrong. Okay. It should not have 144 columns. All right, let's look at the min loadings. Okay, I'll look at the dimensions for that. Okay, why? That did not work. So let's actually look at it. So it gave me 144 columns. So it selected the estimate column, but not, something is awry. So let's look at loadings again one more time. So I got group 2. It's not actually doing the subset correctly, it looks like. So I want to subset out where it's group equals 2. Ah, there's one equal sign. Ah, damn. All right, there's my problem. Okay, so I did exactly what I see students do all the time, and so that's a great example. Totally unintentional, but yay learning moment, where you have to, again, as you're going, make sure you're getting the numbers you're expecting. So let's try that min load again. Now it's 21 columns, so I'm going to multiply the min out. And so let's look at it again. Min multiply. Okay. Oops, sorry. That's a apply function, so it's a list, so I can't look at the dimensions. Let's do those two things and see if it looks like it's correct. There we go. All right. So one bad thing is that you do lose the column names out here because it used the row name from the loadings to give them names, but this looks more appropriate. And if I look at the dimensions of this min multiply now, I'm glad I saw that. Now it's 165 by 21, which is what we wanted. So what I could do here to make my life easier is give everything column names. So I could take this, the names of it here, and give them column names. And so what you do is say call names for men multiply and is equal to the column names for women multiply. Which is then equal to this concatenated list of names. And that's not quite how that function works. I'm going to have to go in and add some more here. Let's sort of hack this together. So if we do this correctly, it should. It looks terrible. Oh no, I just messed that up. All right. Oops. So what am I forgetting? The commas. So it will be very unhappy with me if I don't go in and add those commas. So what I'm going to do, oops, is find this and replace with that in selection. There we go. Now that looks much better. So let's give those column names. So now if I look at the min multiply, now I have column names. It gave the first one a column name with a /n. So apparently I can't hit enter actually between the quotes. I could hit enter at the commas. So lesson learned there. There we go. So just fix it. You see typos and things you don't expect. There we go. Now the column names match. That's not super important, but if you're like me and can't remember what you're doing sometimes, it helps. So all that trouble, and now we can finally get the latent means. So a lot of multiplication, a lot of different pieces, but now we can take those numbers and create the latent scores. So what we're going to do is create latent means. If you wanted to instead create latent totals, use the row sums function, okay, or the call sums function instead of row means. I'm going to use row means because I want to get the average score, because that's traditional. But if you are working with a scale that's normally a total score, do row sums. Okay. And so what we're going to do is get those means for each latent variable and work through one latent variable at a time. So to do this, you have to remember that there are actually three factors here. So going back to the very top here, when we program this DAS model, there is depression, anxiety, and stress. So I can't lump this all into one gigantic factor and create a latent score that's over the overall one. So I need to create three separate latent means for each group. So I'm going to have 6 means in total. Now the cool thing about what I did when I set up the data was I put the data in the order of the columns, or I'm sorry, the order that I typed it in. So question 3 is the first question here, instead of it being 1, 2, 3, 4. And I want to say that I probably didn't have that brilliant insight. Someone else in our research team did. But that does make it a little easier for me to create these row sums. Okay, so what we're going to do is create the women sum for depression, the women sum for anxiety, and the women sum for stress. They do the same thing for the men. And so the way to do that is to use the row means function. And so it's row, and this is one of the super fun ones that has the capital. So it's row means with a capital M. And so I want to apply it to a specific data set. Well, that's the data set that we just created. So the women multiply data set. And what I want to do, though, is I don't want to do everything. So if I take row means and I just do this, what it's going to do is give us the entire sum. So let's actually run that. So if I look at women depressed now, that's all of the people in this data set, so it's kind of huge. Let's just do head. And it gives me every single person's score, but that's an average weighted score across the entire, all the columns. And I don't want to do that. I actually want to do specific columns at a time. So the good thing about adding the column names is I could tell it to just do those columns. So what I could do is say all rows, and then do the C function, so concatenate, and just do column Q3, column Q5, etc. And so pick those specific columns. But since I have them in order, I can actually do something a little easier and do 1, 2, 3, 4, 5, 6, 7. So columns 1 through 7. Because they're already set up that way, where depression is the first 7 columns, anxiety is the next 7 columns, and stress is the last 7 columns. So really, having the column names, other than just knowing what you're looking at, is really useful if you don't reorder the columns. So let's create that women depressed, but only for the right columns. Let's do the same thing a couple times here. And do the next column, so 8 through 14, 8, 9, 10, 11, 12, 13, 14, because there's 7 on each one. And then do the last column, so 9 through 21. Now, that assumes that there are no extra columns on the data set as well. So depending on how you put all of your data together, you just want to make sure that the columns you're using are appropriate. Okay. So I'm actually going to copy this and paste it here. And conveniently, all this stays the same, except I need to take out the WOs and make that all men. Copy and replace. Let's just do the men's data sets now. So now these are named numbers, but they are vectors of data. So what you could do is column bind, so combine together the multiplied data set with the original data set and these column averages. So you could put this all back together into your original data set by cbind function, the different columns together, so then I can use it to predict another variable in the data set. So the cool thing about the way we've done this is that it is you can take that data and mash it into some of your other data. But right now what I want to do is just do a t-test. So base R has a t-test function. It's t.test. And I want to compare men to women. So let's do women depress compared to men depress. And then the other functions for t-tests are alternative. And we want to do two-sided. Okay, so that's a two-tailed P. That's, I'm pretty sure that is the default. But again, it doesn't hurt to know. You could do one-sided. So I think the one-sided one's lower and upper are the options. I want to do paired equals false. Okay, that's also the default. But if you're wanting to do a paired T, so let's say I want to compare women's depression to women's anxiety, that would be a paired t-test. And then if you had some NAs, you would want to do, I think it's na.omit on this particular one equals true. Let me check that real quick. Okay, so let's see. So less and greater for the paired options. Of course, it's not going to say. na.action, just kidding. na.action equals na.omit, I believe, is instead what it should be. Let's try that and see if it runs. Okay, it ran. So I think that's right. And so what that does is it gives you a Welch two-sample t-test. So it's a little different than your normal t-test because the degrees of freedom are estimated in a similar way to degrees of freedom for repeated, like a Mockley's correction. It's not the same thing, but it's the same kind of idea. So they won't be whole numbers, which is a little weird the first time you see it. It is sometimes considered a non-parametrics test, but with the large samples that you need for a multi-group model, they approximate each other. So you can use this type of t-test. There are other t-test functions too, it's just this one's included in base R. Okay. And so what we'll see here is here's the t value, okay, and it's a significant difference between men and women. Okay, so let's do depression here. And so there's my t-test value, which if you're not familiar with APA, you would write like this. Okay, so t with degrees of freedom in parentheses, negative 2.59 if I round up, and then p is equal to 0.01, so that's a significant difference between men and women. Okay. And then it gives me the means down here for men and women. And that's really actually here, so I'm answering this question above, but I can do it here. And I put women first, so women's mean is 1.42. What we're going to do is also calculate the standard deviation here in a minute. Okay, men is 1.56, so men are endorsing higher depression than women, which is sort of an unusual result to find. Let's go back here. But it doesn't give me the standard deviations, which is kind of really annoying. And so what you do is just SD, and then you type the column name. So for us, it's women depressed, so it's 0.44. And then let's do men over here. 0.62. So that gives me everything I need to talk about a t-test except D. So you always want to include some sort of measure of effect size, because when you have sample sizes this large, almost everything is significant. So let's see if that's an important effect, or maybe it's just due to the very large sample sizes. Okay, so that effect size library was F size at the beginning, and it's actually very easy to run. So it's Cohen.d, which will run a traditional Cohen's d with a pooled standard deviation on the bottom in the denominator, which has the it does not have a Hedges correction. You could apply the Hedges correction to it. It's also part of this library, but it does run the pooled SD on the bottom. All right. So what you want to do is type in the names of the columns you want to use, and that's it. There are some other options, but this is the simplest way. And so it gives me an estimate of 0.28. You can say it's negative, but D is kind of absolute, so I'm going to leave off the negative. And so that's a small effect size. And the thing I really love about this this package is it tells you that it's small. Okay, so you're not confused by the negatives, because when I teach basic stats, that's sometimes a problem. And it gives you the confidence interval. So bonus, we, like I've said in one of my other videos, or maybe earlier in this one, I've written a program that'll do the confidence interval for D, which is really neat. And so it was kind of cool to be able to see somebody else's interpretation of confidence intervals, and we're very close. So, like, I'll toot my own horn here. You can use this program, or you can use Moat. They'll both give you the same answer. All right. My awesomeness aside, we'll now do the same step procedure for the other two factors. Okay, so if you have a 3-factor model, you're going to have 3 t-tests. So I'm going to just replace depress this time with anxiety. And if you use this, make sure in selection is highlighted, otherwise you'll replace everything in your document. You don't want to do that. So depress with stress, in selection, all. Okay, right. So that should give us all the numbers we need. Let's test that. So here's my t-test for the second one. So yeah. So that first t would be written as t with 351.64 is negative 0.37. Okay, the p-value is 0.71. We'll get d here in a second. And the women's mean is 1.79. And then the men's mean is 1.81. So those are clearly not different things because it's not significant. So let's get those standard deviations and our d value. Wow, that is really close. 0.61 on both of those, and 0.04 for D. So that's really small. It's effectively 0. Okay. So for anxiety, they're not statistically different. For depression, they are statistically different, but it is a small difference, so I don't know if that's practically meaningful. All right, let's copy this and just edit it. Big fan of copy and paste here. Let's run all this and then type it up appropriately here. So given this output for T, I'm going to cut and paste T up here because I've been doing that the whole time. So the degrees of freedom would be 337.66. My T value is 0.69. P-value is 0.49. And then D was way down here. It's 0.07, so negligible is what it says. 0.7, so not statistically different. The women's mean is 1.97. Standard deviation is 0.61. Men's mean 1.93. And the standard deviation is 0.65. And so now what I've done is I've shown that even though we have a couple of little spots where this scale is non-equivalent, and so actually it's just the variance on one of them, question 21. What we found, though, is that the latent means, the overall weighted scores, one of them is significantly different, but I would argue not practically important because it's a small effect of the difference between men and women. And the other two are not significantly different, and their effect sizes also support the idea of it being practically not important. And so that is how I would calculate a latent means using R, pulling the information from all of the code that we use for lavaan and doing a little bit of matrix algebra magic math to get to this point. But that is a good set of procedures. If anyone knows of a plugin where you can just make that magic happen, please let me know, and then I will do a video for that and be happy because it'll be much faster. Okay. So all of that is multi-group models, including latent means, t-tests, and Cohen's d for a write-up of a multi-group analysis.